In the back?
Can you guys hear in the back?
Yeah.
Okay, good. All right, so welcome to my talk. So I'm going to talk a bit about all.
Hey, Ben.
Yo.
Can you stand up and
I can
speak
stand up.
loudly and clearly? Yeah.
Do I have to stand against the wall? Put my hands on the wall? I will try to speak loudly and clearly, and I will put this in my pocket. So I'm going to talk a little bit about all the crazy stuff that happens on the hardware level. There's a little bit about Spectre in this talk. It's mostly not about Spectre stuff. I did work quite a bit on that as part of my work on V8 and WebAssembly. That impacted us quite severely. But I discovered a bunch of really interesting things about how CPUs work that maybe other people know, but maybe that knowledge is not broadly known. So I'm using this term Turing mirror just in this talk. It's just a figure of speech. You can roughly think of the Turing mirror as another name for a proper abstraction. What that is an abstraction. So imagine that you have a simulation of a program. The program can't tell it's being simulated. It can't see into the hardware state. It can't see any of the emulation which is necessary to run the program. So I basically said that it's a somewhat naive belief that simulated programs cannot observe that they're being simulated. No matter what instructions they execute, what computations they execute, they can only see their own computations. They can't see other computations that are nearby or any part of the machine underneath. And this is a bit of a cartoon definition, right? Nobody really believes computers are like this, do they? Well, people won't say this in words, but they kind of do in deeds. So people might mention stuff about undefined behavior or side channels and things like that, but we kind of always waved our hands and never really took it seriously. But actually, it turns out that it's important in practice. Spectre will show up here, and so I'm going to dig into the details now. So this green bar here, which is my awesome graphic skills here, represents the Turing mirror. So the most important Turing mirror for Spectre is the mirror between machine code and the hardware that actually runs it. But of course there are other mirrors too. There are other perfect abstractions. So between the source language and the machine language, that's supposed to be a perfect abstraction. You can't observe the actual memory contents. You can only observe program values. You can't observe registers and things like that. At least in most languages that aren't C++. You can go up from here, or you can put layers in between too. So you have a source language, maybe it doesn't compile directly to machine code, but it compiles to bytecode, so there's kind of like a Turing mirror there. And then the bytecode might be translated by a virtual machine to machine code. But it also goes the other way too. So from the hardware, actually there's kind of multiple levels there too. So there's a microarchitecture, where you talk about things like register files and register renaming and out of order, like reorder buffers. But those are actually abstractions were implemented in the HDL, and those run on circuits. And circuits, of course, run on transistors. Transistors run on electrons. Electrons run on quantum mechanics. It goes all the way down as far as you want it to go. So to take a look at this, we're going to have to zoom way in, like 9 orders of magnitude in. This is essentially impossible to visualize as a human. I tried here. Every one of these bars is another factor of 10. So imagine just taking one of those 10 segments and blowing it up, doing that 9 times in a row. So if you were to think about that in terms of time, so if 1 second is on the left, a lifetime is on the right. A lifetime is about between 2 and 3 billion seconds. That's about 9 orders of magnitude. So you can imagine, like, if we were to take 1 second of CPU activity, which would be like 4 billion cycles, and we were to talk about that, it might take an entire lifetime to describe that in detail. So there I was, not doing Spectre. This was somewhere in the middle of last summer. I was trying to do science as kind of a side project. What I was actually trying to do, and the reason why I'm going to go down this tangent is because we're going to run into a bunch of architectural details which you would run into too if you're trying to do the same thing. I was interested in measuring super short code sequences. So like single loops. I wanted to see if you could reliably measure a 1% difference in execution time, and just to see what are the characteristics of noise at that level. For that purpose, you can actually read the cycle counter of the CPU, so you can actually see how many cycles go by. Turns out that that's also an approximation. There actually isn't a counter in Intel CPUs, but that's kind of a trade secret. They wouldn't tell me how that works. It's not really important, but you can roughly think that we can see all the cycles going by. And what I really wanted to figure out is, when we zoom out to measuring real programs with real executions, what we see at the small level, is that going to tell us anything interesting about how we should be measuring at the high level? So I basically had a workload, you bracket in some timing, and you vary the workload by exactly 1%, and you should be able to see that in the timing, right? So I assumed, and everybody assumed, I guess, in grad school and undergrad, you kind of implicitly are taught that computers are deterministic. Well, their performance is totally not deterministic. I still believed that I would see deterministic performance if I could zoom in close enough. And I almost got there. But the things that you run into are things like frequency scaling. So the CPU actually changes its clock speed dynamically whenever it decides to because of the temperature or the workload or whatever. Interrupts happen, which means the operating system is servicing some devices. It may switch you to a different core. CPUs actually have multiple hyperthreads which are feeding instructions into the same core. So those are called hyperthreads. So you can actually see their activity. So that's going to cause some noise. You get moved to another core. The cache is also where all the memory accesses are going through. So memory accesses from another program might come in and cause some noise for you. The branch predictor also has some aliasing too. So other programs may inject branch predictions into your execution. Of course, there's memory prefetchers. Then there's memory bandwidth. So all of the other concurrent programs are competing for that bandwidth. And then there's out-of-order execution too. So the first attempt was to run it 100 times and measure that. And then I realized there was so much craziness, maybe I should zoom in closer and run it only one time to see if I could get anything better. And then that was even so bad that I just tried to see how good the timer was. So what you end up seeing, so this is just a download data, you don't actually have to understand what these numbers are, but this is running the workload. So the first group of numbers here is the 100 iterations, and this is 99 iterations. So the first thing that you see is that there's extreme outliers, and they're blatant in the data. So something like 100 iterations of this loop might take 1,500 clock cycles, but then there's this 27,000 one that that's an interrupt. Something happened there. Like, if you were measuring, you probably wouldn't want to take the one that had that interrupt in it if you know there was an interrupt in there, because if you compare that to another execution which doesn't have an interrupt, you're basically not comparing apples to apples. But the interesting thing is that the comparative results actually do check out. So the 100 iterations versus the 99 iterations, as long as you kind of look at a clean sort of set of measurements, and this is 24 measurements here, you actually see essentially exactly a 1% difference. So that was great. Except the problem is, the next thing that you see is that actually, the first few iterations here, the first three or four lines here, the CPU is running at a slower frequency. So it's taking 3,000 cycles to execute those 100 iterations. And then some switch flipped. It happened to be just after we had that interrupt, so it may have been a core migration. But we went to a CPU that was running at 2x the frequency. So now we have 1,500 cycles per iteration. So you can imagine this would cause a problem if you're trying to do some performance analysis and you were comparing one of these lines, which is 1,500, to a line which is 3,000. There's no way that one iteration would make a 2x difference, right? So that was kind of where I was going. I kind of expected to see that. This is what I really hoped I would see, which is basically, notice that the numbers are all different here. This is the same program, same process, but now it's running 700 cycles. But this is super clean, right? There's no outliers here. Within a row, you can see some variance. I'll talk about that if you're interested. But again, if you do the comparative, the comparison between the fast and the slow, you see 1% difference. Great. There's some craziness here, though, in that if you actually dig into the details of one of these groups of measurements, and you do statistics on them, you find out those aren't random at all. They're actually cyclic. So you find things like a run of 11 numbers in a row that may show up repeatedly, and that just doesn't happen because of randomness. What that actually is, I don't know for sure, but what I suppose is happening is there's actually landing in one of a few different states that cycle through, and you get some tearing effects. So you get 740 cycles, 743. There's actually only, in this group of numbers of 24 measurements, there's only 4 or 5 unique measurements in there that kind of cycles between them. So that was kind of interesting. And it also turns out that if you take the minimum and compare it to the minimum over here, you get a 1% difference. If you take the average and compare, you also get a 1% difference. And if you take the maximum, you get a 1% difference. So you can kind of see that it's kind of nice, right? We can actually see this 1% difference that we expected. But stuff can go wrong. So it was all nice. We were in the 700s. That seems like 700. Maybe that's the nominal frequency of the CPU. But then, oh crap, we had a core migration. We see an interrupt, 24,000, jumps out of nowhere. And then suddenly now we're going at 660 cycles. So we jumped onto another core, and that core was actually going faster. And that core gave us another group of numbers. You can see, again, if we were comparing and we didn't know which sort of clock frequency regime we were in, we would get completely confused. Because we should really only compare these 700s to those 700s and not the 600s to the other 700s. Anyway, that was the direction that I was going. It gets worse. So this was on a quiet machine. I had started some other programs to run that were generating some noise, and suddenly you start to see it's no longer 740 and these cyclic behavior. You start to see the noise show up. You get a bunch of new unique values. Turns out that these are roughly 1%, but now you get a bell curve over that. It's not perfect anymore. So that's not really that surprising. It gets worse after that. So you could be in the thousands and then go to the 800s. Anyway, so the point of this is basically there's a whole bunch of craziness underneath. And just by zooming in really close, I could see all that craziness and at least control the data so that I can measure that very small difference in loops. So now we're going to look behind the Turing mirror to see what's going on down there. And the implication is that this precise timer gives me the ability to do that. So instruction set architectures have this architectural state, which I talked about. That's the abstraction, right? That's the registers, the memory, and all that stuff. The program counter. But the actual real state is in the microarchitecture. It's supposedly behind the mirror. You're not supposed to be able to see it except for these performance effects. And there's a lot of it, actually. Once you start reading CPU manuals, there's a couple of CPU people here that we could talk about that. But there's caches, there's instruction caches, data caches. There's a micro-op cache. There's a store buffer, reorder buffer. There's, again, the power save mode of the processor. There's whether this sibling Hyperthread is doing something to the other functional units. Then you've got a TLB, which is for implementing virtual memory. Then there's branch predictors. There's a memory disambiguator. Then there's frequency scaling. It gets madness. It's all madness, right? And then there's prefetchers on top of that. So ultimately, what this means is that if you're a theoretical computer scientist and you think about programs, even pure functional programs, which are functions of their own state, like this is a program here, and this is a program state. It just takes one state and computes the next state. Information about the machine underneath, you can think of it as like a function that has another input. And that other input is the microarchitectural state. And that microarchitectural state leaks information into the program state. And the easiest classic example of how you can get to that is to just read the time. So the timer is actually a function of the microarchitectural state, if you want to go all the way down to physics, if you like. But that gives you a number, and you can start to see information about what's going on. And of course, the performance is a function of the microarchitectural state. It's not a function of the architectural state. So the thing I'm trying to get across here is that if you can measure time precisely, it goes through all the abstractions, all the mirrors, all the way down, at least to circuits. So if we measure cycles, we can see circuit level activity. In aggregate, you might actually be able to see electron activity because the heat of the processor changes the frequency. So over many, many, many cycles, you might actually see like how many electrons are going across the circuit. I didn't actually measure that. I think that's pretty extreme. So there's some facts about these portals, which I'm calling these things that punch through the Turing mirror. Timers are actually pervasive in computer systems. So we know about like reading the cycle counter, reading the date, maybe to the microsecond or millisecond resolution, but you can actually make timers in other ways, which I will show. And in fact, as soon as you have shared mutable memory, you can build a timer which is as precise as the clock cycle counter. These small timing differences, because we're in a fully programmable Turing machine, we can turn any small timing difference into a large difference. So things which would be a single clock cycle, if we're really smart and we know where that clock cycle came from, we can make a program that turns that one clock cycle into an arbitrary number of clock cycles. So that's actually really bad, because as soon as you have a tiny information leak which is exposed in that timing, you can find a program which will amplify that information leak and you can get to that information, even with a low resolution timer. So ultimately what that means is that the resolution of the timer, a low resolution timer does not shut off the information leak, it only restricts the bandwidth of the information leak. And that actually should be worrisome because now we really have to find all of the information leaks and stop them and not just go after the timers. And that's really a problem because computers are stupid fast. So even tiny information leaks, timing differences, we can just hammer on them and we can get to those bits. So it could be dangerous, even these small ones. So in JavaScript, there is a way to get a timer with microsecond resolution that's called performance now. Different browsers has different resolutions, somewhere between 1 and 5 microseconds. But you can also get timers in other ways. So you can use CSS animations to create a timer, which is millisecond resolution. You can use post message back and forth between workers to get millisecond resolution. If you use shared memory, which I'm going to show in a minute, you can actually get nanosecond resolution. You can essentially get a clock cycle counter in JavaScript, all the way at the sort of highest abstraction level. And not only that, so some of these timers actually have some resolution reduction applied to them, specifically for security. You can actually recover some of the resolution of the underlying timer if the way that timer is its resolution is reduced is not random enough. So this is how you do it in shared memory. It's like dead simple. You can do this in 5 minutes. You just have one thread, increment a counter in a global variable, and that's it. Then you can read it in the other thread and just use that as your time. And that has extremely high resolution. It works even better if you can get that timer thread onto the same core that you're on. So if it's running on the same hyperthread, you can get this time location where that counter is into the same L1 cache. So now the thread that's incrementing it doesn't actually have to pull that cache line out from the thread which is trying to read it. So you can actually get much better resolution. So the way I did this in like 15 minutes, basically you just have an array of counters, you have that many threads, and then over here you can actually figure out by the resolution of the observing the timing values, you can tell which one is running on your hyperthread. And it may change, so you may have to find it again, but you can basically get down to essentially 3 clock cycle resolution this way. So like in the middle of this interesting side project, doing all this, Spectre shows up. We had to deal with it, and now like all that stuff about the microarchitecture and the high resolution timers, which I just happened to be doing because I was interested, it all just comes into play. So this microarchitectural state is not only determines the performance of the program, it also has information. It has information that you can write and you can read. So one way to do that is you can touch a cache line and make that cache line fast. So later when you touch the same cache line, whether it's fast or not, it gives you information. So now through the mirror, we not only read, but we can also write. That should be a read there. So Spectre has many variants. So I'm not going to talk about them except this variant 4 at the end, because that's where most of the work that I did comes in. But variant 1 is basically deals with branch prediction. So you can train the CPU that, hey, my bounds or my array indexes are always in bounds, and then the CPU is going to predict that your new index, which is way out of bounds, is in bounds. And it's going to execute your code as if that was in bounds. And using that mechanism of disclosing information to the cache by essentially hiding information into the cache, which you would not normally have access to, but you did have access to in speculation, which is normally rolled back, you can basically exfiltrate that data. So that was what variant 1 was about. Variant 2 was targeting a different branch predictor, which is for indirect branches. So you could actually train the indirect branch predictor to go to essentially any code that you want. So then you can program an indirect branch to go to a speculation gadget which discloses information. So there's some details there though, which I'm not going to go into, but variant 2 is also very bad. Variant 3 was mostly about doing this across processes because you could essentially read kernel memory. There's other predictors in the CPU too. The RSB, the return stack buffer, deals with predicting return addresses. So you could trick that thing and and get a gadget the same way. Also, CPUs have a mechanism by which they don't eagerly restore FPU state when you switch between processes. So the old FPU state was actually still there, and they would trigger a fault and ask the operating system to page it in. But in the meantime, you get to see the old processor state. And the old processor state of another process, which was the FPU registers, which is typically where you put your RSA keys, which is terrible. So that was the lazy FPU restore. And there's another one about how the processor traverses page tables. Again, CPU designers thought you could never see any of these mispredicted things because all the architectural state was rolled back. But again, you could essentially read all of L1. So variant 4 is the one that I'm going to talk about. That's speculative store bypass. That's actually the only one of these that depends directly on the out-of-order execution. All the rest of these, you only need to have branch prediction or safety checks for address spaces. So I had to kind of realign my mental model about how CPUs work. So you kind of think about machine code executing in a line. It takes a branch, it goes somewhere, and then the branch goes somewhere else. And it's kind of like this thread going through the code. This is absolutely not how CPUs work. CPUs essentially have a warp bubble. The warp bubble is the reorder buffer. So the CPU is actually not executing your code here. It's actually executing your code in the future. So it's actually fetching instructions maybe 200 far out in the future. And it knew that path by predicting all the branches that led there. But what it is actually doing is it's committing the instructions as they're finished in the program order. So there's like in the middle, there's this buffer, which is literally called the reorder buffer, where all the instructions that it thinks you're about to execute get thrown in. In that buffer, the CPU knows data dependencies, but it has forgotten control dependencies. It doesn't actually know what instructions depend on what branches. So it can just execute them even if the branches aren't even true. It just speculated that they were true. And it turns out that it also just speculates that the memory dependencies aren't there either. So what that means is that if you have loads and stores that depend on each other, it may just assume that they don't depend on each other. It may execute them out of order. And that's going to be a problem. So just to illustrate that, in the reorder buffer, there are some instructions which have already been executed and will be committed in program order. There's some that are ready, and then there's some that are not yet ready because they have data dependencies. So when the CPU actually commits a branch, not when it executes a branch or fetches a branch, when it commits a branch, that's when it knows that it was actually correct or not. And if it was incorrect, an incorrect branch prediction, all of the stuff in the reorder buffer is thrown away. Well, in theory. We don't know exactly how it works, they won't tell us, but in theory it throws away everything in the reorder buffer. Nobody saw anything, it's all fine, Vegas rules, what happened in speculation stays in speculation. But again, something leaked out, right? It's through the microarchitectural state, and that's the real problem. So this is variant 4. It's like dead simple when you see it. So it only takes 2 instructions to exploit variant 4. We have a store and a load, and we have 2 addresses. We have X and Y. So if X is not equal to Y, it's absolutely fine, other than memory model considerations, but let's just assume that there's no atomic operations here or any barriers. If X is not equal to Y, it's totally fine to execute the load first. But if they are equal, then this is going to be a violation, and we're going to have to back that out later. So, again, with the reorder buffer, it may know Y, but not know X yet. It may not even be able to tell if X is equal to Y, so it may go ahead and execute the load first. So the problem is that if at runtime X does actually equal Y, the processor will execute the load first and load from memory, a stale value. So later, when it's going to commit those instructions, it's going to check that there's an aliasing relationship, and if that was wrong, it's going to throw it away. But meanwhile, it got the stale value from memory. So this is bad, right? We read a potentially secret stale value from memory, and it's too late. The stale value could have been used for this nefarious purposes. We could have, if we knew this was happening, we could have disclosed the stale value through the microarchitectural state. It gets worse, right? So we didn't just read.
Sorry,
Yeah.
So the program can actually observe the stale value, even though that violates the memory model?
Right. So what you can do is, since the load is executed and now you have that stale value in RAX, you could use RAX as an index into an array and then touch a particular cache line based on that value. And then you disclose some information about that stale value.
Okay, yeah, so the normal control flow wouldn't see it, but we see it as a side effect of something else.
Right.
On the specific.
So there's no control flow here. It's just memory aliasing.
Yeah.
So if the attacker knows about this and knows about that the CPU is doing this thing, now the smart attacker just puts a pointer that it wants to use where that stale value is going to be, and now they can use this little gadget, which is only 3 freaking instructions, to read anything in memory, and then leak it through speculation. So now you have a gadget to read all of memory, and that's terrible. We don't want that. So I wanted to take a look deeper in variant 4. I want to understand under what circumstances the CPU would do this memory disambiguation. You get it wrong. Is it actually a threat? So I built a microscope, a virtual microscope, and tried to do science. I kind of actually felt like a scientist doing this. I wanted to show this order of magnitudes graph again to give you an idea of how small of time differences we need to be able to measure in order to be able to do this. So in terms of cycles, so one cycle, an L1 cache hit is about 3 cycles on a modern CPU. L2 might be around 12 cycles. L3 might be around 50 to 100 cycles. DRAM might be out there in the order of a couple hundred cycles. So if we can measure the difference between an L1 hit and DRAM or L3, then we can essentially get our bit. Well, the problem is that I started to build a system to do this, and then you find out that actually caches do not have the latency that is in the published literature. And this is because of all the noise and all the things that I showed you before. So if we were just to think about this in terms of probability and where this bell curve comes from, what they tell you in the manual is that the access latency is 80 cycles. That is in the absolute best case. If the CPU is running at its nominal frequency, if you have bandwidth, because the cache also has bandwidth from the CPU, if a whole litany of random variables, right? So if all those variables are right, then we get 80 cycles. If even one of them is wrong, we start to move away from that 80. And if an average case, some of them are wrong, so we end up with this median number here. So more things go right, the faster we go, the more things go wrong, the slower we go. So what that means is basically the things that they tell you in the manual actually are the fastest thing, and these things start to overlap. So we may not necessarily be able to tell L1 from L2 with any really good probability. Oh yeah, and the other thing that happens is all those other things that I saw when I was trying to measure that loop, they're in there too. So core migration, it might take 1 million cycles because you went onto a core that has nothing in its cache and a whole bunch of other stuff has gone wrong. The operating system is stealing your pages all the time, so you might get a page fault through no fault of your own. The operating system doesn't have your pages, so you get some latency because of that. The operating system is servicing all kinds of devices and things, so you get interrupts. You might miss the TLB because the TLB also you also need to get a translation to be able to access the cache. So what I came up with is basically to divide the space into two categories, fast accesses, into 3 categories actually. Fast accesses, slow accesses, and something in the middle where I'm not sure. Some noise has caused either this to be too slow that I'm not sure anymore that it's a hit, or it's caused something to be so fast that I'm not sure that it was a miss. So then we get into the cache. And now you actually want to use the cache as something which you want to control. And now it's fighting you. And the principal way the cache fights you is the prefetcher. So the prefetcher is trying to figure out memory accesses and cache lines that in the future they may want to use. And there's a number of different prefetchers in modern CPUs. One of them tries to take data from the L2, which is near L1 cache lines, that you already have in L1 and fills them in. So basically on Intel chips, cache lines are 64 bytes wide, and those are divided into pairs of 2 cache lines, which are 128 bytes wide. And if the CPU has enough bandwidth right now, it will go ahead and fill in the half that you don't have. So if you're trying to do something where you're doing neighboring lines, you may be completely confused because the CPU has just prefetched one of those lines for you. It also has a little predictor in there which is keyed on the IP, so it actually is trying to figure out what does this instruction fetch next. So there's like a little mechanism in there which is trying to figure out what accesses and loops, for example, will access next. And then the L3 also has like several prefetchers in it too. It can actually tell that you're doing strided accesses through memory, and it will fill in the dots so that it will fill in the lines which are the next in the sequence. And it can track multiple sequences at once. It can know, for example, track 7 different access patterns through memory. So if you're actually trying to control the cache, the prefetcher is the main problem. There's also LRU replacement. So if you don't have a way to flush a cache line, thankfully on Intel CPUs there is a CLFlush instruction, then you need to implement a way to evict cache lines. So you have to understand the algorithm by which the CPU actually replaces cache lines in order to kick cache lines out. Caches also have set associativity as part of the cache geometry, so you have to know what line aliases another one. There's bandwidth between the caches, so there's only so many lines that you can be accessing at a time, so that can cause some noise in here too. And there's a whole bunch of other stuff. So to make this microscope, to be able to study this variant 4 vulnerability, I came up with the idea of basically, well, it's not my idea, but you use a timing area where the cache lines, which cache line it is, encodes values. So you can, for example, if we assume that a cache line is 64 bytes, we need about 200 kilobytes of memory in order to make a space of memory where this line encodes 0, and this line encodes 3, and this line encodes 255. So we can encode 8 bits of data in the cache that way. So if this line, for example, 3, the third line is fast, that means that value, that value is a signal in the cache. And because we use a whole area and not just 1 or 2 lines, we can actually encode multiple signals. So we can see that 3 and 5 are both fast on purpose. So the first thing about that is that you don't want to use lines that are next to each other because of all these, like the buddy filling that the L2 to L1 prefetcher does. So we have to spread them out. It turns out a stride of a prime number works pretty well. The smallest one that I found that worked pretty well is 13, but you can use other numbers there too. So the next thing is that there's this stride-based prefetcher in the L3 cache. So if you were to imagine that you're going through the timing area after you've put some signals in here, and if you just start touching them, are you fast, are you fast, are you fast, the prefetcher will go ahead and prefetch lines in the future, and you'll be confused. So I basically implemented pseudo-random probing, right? So you start at one of these random offsets, and you do like one of these multiplicative random number generators. So to the prefetcher, it looks like you're accessing random addresses, but you're really just going around. That's enough to defeat that prefetcher so that it doesn't ruin the information that you've got there. The next thing I discovered is that you can have, after you've done this entire probing, that's enough accesses that when you come around this whole loop again, after you tried again, the prefetcher might actually remember across iterations, even though you've done this pseudo-random thing, it may remember this load from this time to the next time. So to defeat that, you just rotate over by 1 line. So now you're accessing totally different addresses. Prefetcher doesn't know. The next thing I discovered is that if you, for example, you're using 255 sets of lines to encode information, you want to actually time them, and you need to put the timing data somewhere. So if you put the timing data in the actual lines, you don't use more lines that cause more confusion here. So if you just actually measure the time to access this line and store it in that line, it works much better. And the other thing that I discovered is that you can imagine that thanks to the CL flush instruction where you can pick a cache line and say, CPU, I don't want you in the cache anymore. You could imagine that after you've read the information in the cache, you just flush each line. I found that actually you need to flush the lines around it too. Don't know exactly why that is, but what I do is just flush the entire thing. So now we've built this thing. We've defeated all the prefetchers. There's still a bit of noise in the system, but you basically get about 4 nines of reliability. So if we didn't do any of that stuff and any of that rotation, you essentially get 10% reliability. If you do 1 or 2 of those things, you can get to 90. Then if you do the next thing, you get to 99. So I got to about 4 nines of reliability. That's enough to be able to tell reliably whether there is something encoded in this channel with high enough probability to rule out false signals. So if we have this experiment code over here, what I typically did is I would write what I call a carrier signal, which is some value which I would always expect to be in the channel, and then some other speculative value which I want to disclose. And the reason why that is then I can tell if something's going wrong. So then I can basically have the reliability of the channel built into it. So for example, like if we were doing this code over here, and I wrote a 0 in there, and I was trying to execute some vulnerability, and I didn't see a 2 in the channel, that meant there was no leak. Whereas if I saw a 0 and a 2, that's a high confidence leak that whatever speculative thing that I was trying to do here to make this 2 appear actually was working. It can also be the case that other things started to show up too. That means maybe there's some noise in the system, maybe we're somewhere in that middle region, so it's lower confidence. If you see something else that you weren't expecting, something suspicious, and something's going on that you don't understand. So that happened a lot. And if you just see a bunch of these things, that's just noisy, and it could also be broken. So we found a lot of interesting things about how the memory disambiguator works. I don't think that we discovered anything that that Intel would agree on how it works, but we had a folk understanding of how it works. Because of complicated NDA situations, I can't even tell you my folk understanding of how it works. So I can't give you any more details on that. But I can tell you that variant 4 is really nasty. It's totally exploitable, and that's bad. And also, we worked really hard, Phil worked really hard on trying to do software mitigations for variant 4. And it's essentially infeasible. This is why Intel has microcode updates which can disable the memory disambiguator altogether. Okay. So I also want to talk about amplification. So I mentioned that small differences in timing on the order of 1 cycle or 2 cycles, they seem innocent, right? Who could possibly measure that? If you don't have a high resolution timer, how are you going to be able to do that? Well, it turns out that even those small differences you can amplify to essentially arbitrary resolution. So we saw that L1 cache hit is about 1 nanosecond, so like 3 cycles, versus a main memory hit, a main memory access is about 100 nanoseconds. So if we have 1 microsecond resolution, we should be safe, right? Well, the problem is that you can just bulk up multiple lines. So if our vulnerable gadget comes up with a secret bit, we can use the secret bit to access either lines A through N, A0 through AN, or B0 through BN. So you can think of this as disclosing this secret bit into the cache, and then we measure a whole bunch of lines. And now we can get to a much larger timing difference between 0 and 1. But the problem with that is this is limited by the cache capacity. You can only fill up the cache with so many lines before you run out of lines that could be in the cache. But even so, we were able to get this up to 600 microseconds. So this is like a fundamental irony of caches, right? The bigger it is, the more information you can store in them. And the bigger you can make the timing difference because of that information. So it gets worse. So not only can you amplify it up to the limit of the cache capacity, you can also amplify it arbitrarily. And it's actually really simple to do that. So again, if we go back to this gadget where we have a secret bit that we want to disclose in the cache, we can just read A or B depending on the secret bit, then we immediately read A. So what that means is that If the secret bit is 0, we're going to read A, and then we're going to read A again. So that means we have a miss, because we assume that A is out of the cache, and then we have a hit. But if it's 1, then we read B, and then read A, and both of those are misses. So now we have 1 hit and 1 miss, versus 2 misses, and we can just do that as many times as we want. So we just set n to be as big as we want, and then we do that over and over and over and over and over again, and then we just do the measurement. So no matter what the clock resolution is, we can get ourselves over that threshold. So that's really bad. So it really doesn't matter what the resolution of the clock is. We can do this. So in visually, what that means is that we literally were able to move from these order of magnitude, about 5 order of magnitudes over, to make a miss and hit be on the order of milliseconds. And if you use arbitrary implication, you could make it seconds, if you like. So the conclusion that I want to get is basically computers are super weird. The closer you zoom in, the weirder they are, and they're actually pretty interesting and fun. When you start looking at timing with a high resolution timer, high precision timer, you see all kinds of amazing details. All the fasterizers, all the optimizers can be measured, and hopefully you can understand them too. I was able to understand a few of them, but not all of them. Now that Spectre is out and information leaks come through timing, all of this is terribly relevant, and we should do some more science about it. Thank you.
So great talk. I have actually kind of stupid question. Why were you actually at an NDA with Intel?
The entire company is.
Or the entire company?
Yeah.
Okay. Because you were doing science. It seemed that didn't really require any insights into
NDAs. So the way company is very standard, like company NDA to an NDA between two companies. Even if I discover something that's not given to me by an Intel engineer with any specific knowledge, that's still covered under the NDA.
Okay.
So, you speak about the exploitability of fasterizers. Your focus here is on hardware level optimizers, but almost every virtual machine, I'm sure, or JIT has some kind of on-the-fly optimizer. Is there any relevance or lesson that you think for those in this room who are implementing that kind of system for how to avoid exposing things that could lead to this class of bugs?
Yeah, so the question is about virtual machine optimizations. So in theory, yes, any optimization at any level between any of those like pairs in the Turing mirror kind of hierarchy could be exploitable. As far as advice, I think the hardware's on fire, so there's so much action happening there that like JIT compiler optimizations and leaking information through that, it may be possible, and I have no doubt that in 5 years' time there will be papers about that. But I don't think it's a crisis just yet.
What do you think is the way forward in terms of avoiding everything being on fire?
Personally, I think that we will probably build computer systems where there are separated hardware chips, where there are dedicated hardware chips which essentially run today's applications and server applications where there's one trust domain, and their side channels don't matter because all the code runs in the same sort of space. And then there may be dedicated chips for running code which is untrusted. Maybe they don't do speculation, maybe they don't have as many optimizations, and there might be several such domains. That's my personal view. It's the only way. I mean, shared resources means that there's covert channels. It means there's information leak, and there's tons of information leaks here.
And going back to the beginning of the talk, you mentioned that it was very hard to precisely measure timings. And as scientists who often need to precisely measure performance for the things we're working on, do you have any tips on how we can be more accurate?
Being more accurate. So I think the The most important problem that we have now is not the accuracy of measurement, it's the methodology to compare measurements. So as you saw, like, there's several clock speed regimes, and if I was careful and I compared measurements from one clock speed regime with the same, I could easily see the difference which I had programmed in. But if I compared the wrong measurements, then it becomes lost in the noise. And statistically speaking, you could think about, like, we take all the measurements with all the clock frequencies, domains, regimes here, and all those over here, and we have tons of them, and then we do statistics, and that 1% also pops out, but you need way more measurements. So I actually think that the methodology we use to compare is more important than how we measure. So we have the technology to do precise measurements. We don't have the methodology to classify those measurements and understand the variables that go into them.
Isn't there a problem reading the timestamp counter in a multi-core system, or that was solved and it's now mostly transparent?
So operating systems do try to align them so that the timestamp counters from one processor to another are pretty close. But if you get migrated, there's going to be 10,000 cycles. So there's always going to be a bump there. Typically, you kind of hope that you stay on one core while you're doing your measurements so that you get a consistent.
Okay, so the good strategy might be like run it and detect this core migration and just throw away that result.
Yeah.
I mean, for folks doing measurement, it's also worth noting that there are tools that will, for example, turn off frequency scaling on a machine, which you probably don't want to do on your laptop because it might melt your laptop down, but which you can do on the desktop machine. And there are tools for gluing your program to particular cores or particular threads and make sure that, for example, you are not co-scheduling multiple threads on a single core.
So you've mentioned NDA thing, and my question is, there are some vendors who produce CPUs, right? There are some other vendors who produce software. So what do you think could be done to avoid situation when something is discovered, right? But vendors might want to avoid making it public to save their reputation, right? So is there any way you could see how this could be more open to community?
That's tricky. I think so in particular, like Spectre was disclosed on the timeline because of the way Google did research into this, and they had their own disclosure guidelines. But if like an independent researcher finds something like this, then it's kind of a crapshoot. How the disclosure happens is complicated. I think having open tools and having open test cases and also open hardware will make this easier. But I don't have like a really good answer to that.
What do you think about threads getting added to WebAssembly? Does that increase the danger?
Yes, unfortunately.
The process that you had for discovering these vulnerabilities, you described here, and the choice of experimentation, kind of searching out how to do this, do you feel that this is an automatable process?
Yes, actually, I think I kind of have this hope that machine learning will give us the ability to understand all those like relationships. So as I mentioned, there's like cyclic behavior in some of those measurements that I did. I imagine that there is a state machine, which I'm hitting up against, that I kick into one state versus the next. And a machine learning algorithm, for example, can find relationships between variables and tell me why that state machine exists or which thing I have to poke. So I think automation is the only way that we will be able to understand the fine details of things like this. All right. Well, thank you.